Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the Electrical Engineering channel. In this lecture, I will start my discussion on numerical differentiation methods. So, numerical technique to solve ODE of the form dy by dx equal to f of xy is called Euler's method of differentiation, and y0 is equal to y naught. Initial condition is also given to us, and h is the step size, and x is equal to 0, which is equal to x naught is the initial condition, and f of xy is a function, and this is actually the slope of y with respect to x. So in Euler's method of differentiation, we have to write out down the first order differential equation in this form. So only the dy by dx term will be at the left hand side, and all other terms will be shifted to the right, and all of those terms combined together are represented by f of xy. So this is a function which has variables of x and y. Okay, so it means that f of xy is basically the slope of y with respect to x, because f of xy is equal to dy by dx, and f of xy is equal to slope of y with respect to x, and f of x naught y naught is equal to slope at x is equal to x naught. Y naught and x naught is the initial condition. Y naught is the initial condition of y, and y0 means x naught is equal to 0. So x is equal to 0 or x is equal to x naught is the initial condition of x. And here you can see this is our x-axis and this is our y-axis, and this is our original solution of the ODE, which is actually y. So y is the original solution, and we have to specify the step size, which is h, and depending on the step size we will evaluate the next values of y, right? So y0, y1, y2, y3, so on up to the final point. So that's how we will evaluate the next values of y, and we will plot them, and the original solution will look to us like this. And if we specify the step size to be high, then we will get the solution in the form of this straight line. So the step size should be as small as possible, then we will have such a curved solution of the differential equation. So let's discuss all these things in detail. And dy by dx is equal to f of x naught y naught. This is the initial condition, and dy by dx means y1 minus y naught divided by x1 minus x naught. This is equal to f of x naught y naught, and x naught and y naught are known because these are the initial conditions, and we can evaluate our function at the initial values of x and y, x naught and y naught. So this function is known, y naught is also known, x naught is also known, and x1 can be evaluated. X1 is equal to x naught plus h, or x1 minus x naught is equal to h. So this y1 can be written as y1 equal to y naught plus f of x naught y naught multiplied by h. So x1 minus x naught is equal to h. Similarly, y2 will be equal to y1 plus f of x1 y1 at h multiplied by h. So we know all these values, so we can evaluate y1, and now we know all these values x1 y1 and f of x1 y1 can also be evaluated. We know h, so we can evaluate y2 and so on. So we can evaluate all the values of y, and then we can plot them, so that will give us the actual solution of the differential equation in the graphical form. So we will get the solution in the graphical form, but not the analytical expression in numerical differentiation. So we will solve this example one. So this is a very simple example, and in this example we have to represent our differential equation in this form. So we will keep dy by dx term at the left hand side, and all other terms will be shifted to the right, and this is the initial condition. So this is our f of xy, and this is our dy by dx. So let's solve another example. So this is example 2, and d theta by dt is equal to minus 2.2067 into 10 to minus 12 theta raised to power 4 minus 81 into 10 to 8. This is the initial condition. So this is our f of t theta. This is our function, and our variables are t and theta. Theta 0 is equal to 1200 Kelvin. So this is our um, t naught, right? And this is our theta naught. So initial conditions of t and theta are given to us. So theta I plus 1 will be written as theta I plus f of t I theta I into h. H is the step size, and I is for I is equal to 0, t naught is equal to 0, and theta naught is equal to 1200. So theta 1 will be equal to this expression, and put the values of theta naught, evaluate this function at t naught, theta naught, and h is kept as 240. So theta 1 is equal to this. Similarly, we can evaluate theta 2, which is equal to theta 1 plus f of t1 theta 1 into h, and that will be equal to 110.32. And similarly, we can evaluate theta 3, and all these values are actually summarized in this table. So for a step size of 480, this is our theta value, which is minus 987, and our error is equal to 1635.4, and our percentage error is 252.54%. Now we will evaluate all these values of theta for decreasing step size. So if we keep the step size to 240, our theta value will be equal to 110.32, and this is actually the final value, and the error is equal to 537.26, and this is percentage error. If we keep the step size to 120, our theta evaluated final value of theta will be this value. Error is equal to 100, and percentage error is equal to 15.566. Now let's further reduce the step size. Our theta is increasing, and it is matching the actual solution. This is our error, and this is our percentage error. And for a step size of 30, theta has further increased, and error has further reduced, and percentage error has further reduced. It means if we want to solve an ODE using Euler's method of differentiation, our step size should be as small as possible to get the minimum error. Okay, so now the thing is that why do we get high error for higher step size? So if we keep the step size higher, why do we get more error in Euler's method of differentiation? So let's evaluate first the exact solution using Taylor series. So if we use Taylor series, then our next value of y will be equal to current value of y plus derivative of y with respect to x into xi plus 1 minus xi plus 1 by 2 factorial d square y over dx square xi plus 1 minus xi square plus so on. So this is the evaluation of the next value using the Taylor series expansion. So yi plus 1 is equal to yi, dy by dx is equal to f of xi yi, and this is our step size, plus 1 by 2 factorial. So double derivative of y with respect to x is actually single derivative of this function, because single derivative of y is equal to f of xy. So double derivative of y will be f derivative of xy multiplied by this square plus so on. Now in Euler's method of differentiation, we have just considered these first two terms. We have neglected all these higher order terms, and we are saying that yi plus 1 is approximately equal to yi plus of f of xi yi multiplied by this expression, and we are neglecting these higher order terms. So if we want to neglect these higher order terms, then our step size should be as small as possible, because this is our step size. So if this step size is as small as possible, then these higher order terms can be neglected, because if the step size is small, its square will be even smaller, and its cube will be even smaller, and so on. So our general solution will be equal to the sum of these two first terms. So if we want to neglect these higher order terms, our step size should be small, and if our step size is large, then we will see considerable error, because error is equal to all these neglected terms, and these neglected terms will yield significantly higher values for higher step sizes. And if we have higher error, then our solution will not be that much accurate. So Euler's method is not very accurate method, and it will give you the accurate result only if you have kept the step size very very small. Then these higher order terms will be neglected and our error will be equal to 0 and our solution will be equal to the sum of these first two terms. So I think that thing is understandable to you now, and let's solve this example. And in this example we are given this integration definite integral and we have to solve using Euler's method. So this is our integrand and we can write it in the differential equation form. So dy by dx is equal to 6x cube and this is the initial condition, and y5 is equal to 0 and this is equal to f of xy. So in the first step we have to consider the step size of 1.5. So there will be two steps, right, from 5 to 6.5 and 6.5 to 8. And for I is equal to 0, x naught is equal to 5. So this is x naught and this is y naught. X naught and y naught are given. Step size is also given. X1 is equal to x naught plus h, which is equal to 6.5. And y1 is equal to y naught plus f of x naught y naught into h. Y naught is equal to 0. And function value at x naught y naught is equal to 6 into 5 cube into 1.5. So this is equal to 1125 and this is approximately equal to y at 6.5. In the step 2, I will be equal to 1, x1 is equal to this, y1 is equal to 1125, which is just evaluated, h is equal to 1.5, x2 is equal to x1 plus h, which will be equal to 8, y2 is equal to y1 plus f of x1 y1 into h. This is y1, this is f of x1 y1. So x1 is equal to 6.5, so 6.5 cube into 6 multiplied by h. So that will be equal to this expression, and this is approximately equal to y8. So this integral from 5 to 8, 6x cube dx is equal to y8 minus y5, and that will be equal to y5 is equal to 0. Okay, so that will be equal to y8. So 3596.625. So this is how we can solve um, differential equations using Euler's method of differentiation. And the only thing in Euler's method of differentiation is that the step size should be as small as possible because we are actually neglecting the higher order terms and we are just considering the first two terms. So I hope you have understood this concept. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.